All right, so I'll be talking about the one of the previous work we have done related to streamflow forecasting with temporal fusion transformers. This work was published last year, like in 2024 May. It's been a while, like I haven't had a chance to work on these transformer networks or any attention networks after that. So in the presentation, we'll be starting with some background. What was the motivation and objective of this work? And the three models that we set up. Then we move on to the experiment one, the first experimental setup where we implemented all these three models in a streamflow forecasting setup to predict the future stream. And we'll discuss some results from that experiment. Then the second experiment where we set up this more sort of a rainfall runoff modeling to predict or to simulate the current step runoff based on meteorological variables. And some results from that experiment and some key takeaways. So going to the background of this study, like as we know, the recurrent neural networks and attention-based networks are, two key model architectures that are being used for sequence prediction. So in RNN, like recurrent neural networks, it has been very successful in hydrological modeling, especially the LSTM. However, there is no direct access to distant data, meaning in LSTM, like it process the data like in a step-by-step or in a Markovian manner. So there was an issue, like to find or to get the information from very past or, like let's say 1 or 2 years behind data. On the other side, in attention networks, we have, the model have access to the entire sequence of input data, but it does not have a Markovian nature that is rooted in hydrological systems. So there is no state evolution over time in attention-based neural networks. So what we thought is, why don't we combine both of these aspects? And we hypothesize that the combination of attention and recurrence that could improve streamflow prediction because it combines, the plus and minuses of both these type of architectures. And to test that, we use a model called temporal fusion transformers. We'll get into the model architecture in coming slides. So this model basically is a combination of both LSTM and attention neural networks. So with that objective, we set up three models in this study. So three models that belongs to each category. One is recurrent neural networks, one is attention, and one is the combination of both. So in recurrent neural networks, we went with a classic LSTM, nothing fancy there. And in attention neural networks, we used a basic transformer networks. I think by now, like everyone will be familiar with the architecture and with the working of this particular model. And for the combination of both attention and recurrent neural network, we implemented this model called temporal fusion transformer. So when you look at this model, it's basically a combination of LSTM and a attention layer that is stacked on top of that. Although there are a lot of different connections and components here and there, the basic architecture is just an LSTM and a attention on top of that. These both networks are connected in like in a very complex manner where it can take the static covariates of each basins, and it after processing through a static covariate encoder, that uh, like encoded static information from the static covariates is passed to different parts of the new model architecture. Before LSTM, you can see a variable selection networks in the TFT architecture. So what this variable selection network consists is basically it that variable selection is shown in the figure C in this particular model architecture. So what happens here is like it passes all the variables. I mean each variables at time t through a gated residual network, which is represented on top of this figure. And at the same time, it also passes a flattened version of this, which is represented using this symbol. So this flattened version will go through a different gated residual networks, which then gives a vector called Vx Vk of t, and that is just taken. We just do a dot product with the outputs of each variable. So in essence, what I'm trying to say here is like this vector Vx or Vk is, it's a like a weight given to each variable. Like it's a like that can be interpreted as a variable importance or the relative importance that the model assigned during the training process to each variable. One another point to remember is like the like although like in the figure there are different multiple variable selection shown, it is just one like one variable selection network because all the weights are same. There is a weight sharing between these blocks in the model. And after passing through LSTM encoder, so the model setup is in a way that there are two LSTM. One is LSTM encoder and one is LSTM decoder. So LSTM encoder is one network, and the hidden states is passed to the LSTM decoder in the right hand side of the model architecture. That is like very basic, as we see in a basic LSTM. This is same as that basic LSTM, and from each time step we take that output of the LSTM layer, and after passing through a gate and normalizing, again we pass through a gated residual network. This gated residual networks are like induced in every part of the model architecture. I think that helps in a better processing of information. However, like after passing all these gate, the outputs of all this LSTM finally reaches to a attention layer. So you can see like the LSTM outputs, the entire sequence is then seen by an attention layer, and the model can like learn from all the sequences, all the processed sequences using this multi-head attention. And finally, we try to predict the stream flow of the next day. So the input here is like past 365 days of like meteorological variables, as well as we provide the past stream flow also. So this is more sort of an auto-regressive setup. And we try to predict the stream flow of next day. Yeah, I think, so like we can discuss further about the model architecture if there is any question or anything. Yeah, so with these three models, now like let's let's see how we set up the first experimental for streamflow forecasting. We start with the caravan data. We use the caravan data at that, at that time of the study. I think there are a lot of additional basins currently available. So the caravan data is filtered using, we only took less than 30 days of basins with less than 30 days of continuous missing data. And we filtered further using basins only with at least 30 years of data. And after both these filters, we ended up with 2,610 basins. From these 2,610 basins, we start with one basin. We split it into 70, 10, and 20 ratio for train, validation, and test, basically. And we took 38 continuous variables, 209 static variables, and the past stream flow of last or previous 365 days. So the idea of providing all the information, this was the all, full set of variables that was available in the caravan dataset. So the idea was to provide all the information to the model and let the model figure out, what information it could learn. And the same set of input is passed to all the three models to predict the next day's stream flow. Now this is for one basin, and we implemented this setup to all our 2,610 basins. So there is one key disadvantage was there was each single basin, each model was trained based on one single basin. That means it was not collectively trained, or it was not like one model for all basin. So there will be three models for each basin. And now, yeah, it is repeated for all the 2,610 basins. Now, the results we obtained, this is the distribution of KGE on the test case. The median KG for LSTM is 0.68. Median KG for transformer was 0.66, and for TFT 0.70. So in this particular setup, we see transformers. TFT performs much better than LSTM or transformer. And also, like on the number of basins that have like really good performance, near 1 kg is higher in case of TFT. We looked into the performance variation with respect to different catchment attributes. So here, when we look into the performance variation with respect to the mean elevation of different catchments, we see that like TFT performs well in all cases. Also, like the transformer or the attention-based neural network tends to, perform much better as we go into higher elevation. The potential reason could be like in basins with at higher elevations, the hydrological response time would be much higher, because those basins will be dominated by snow process and slow rainfall runoff dynamics. So in such cases where the response time is lower, the attention can take advantage, because it can learn from it have access to the whole sequence at a time. This is again the attention distribution that the model gives for the past time step for like each month. As you can see, like on the immediate past as well as like the previous 1 year, like near previous 1 year part of the sequence is getting much, more importance in terms of attention. So like uh, due to the seasonality in this rainfall runoff process, like there could be information like that leads to a particular value of stream flow. That means, let's say we are trying to predict a value in January. So the rainfall runoff process that happens, in the previous times of like maybe in December or maybe in November, that has information. The same time, something that happens previous years December or November, that could also provide some information in that particular rainfall runoff dynamics. One key importance or like the advantage of temporal fusion transformers is it is interpretable. We can unbox the black box and see like why the model predicted the value it predicted. So this is just a sample feature importance for one basin. As you can see, like past stream flow is like much important than any other variable because of this autoregressive setup, and followed by total precipitation and some like soil moisture, then potential evaporation like that. Also, it gives a importance for static inputs. So that was the experiment 1. Now, like we set up the models in a different experimental setup where we were more focused on the rainfall runoff modeling or rainfall runoff simulation, where if the model can learn the dynamics of rainfall to runoff process rather than just like an autoregressive prediction. This is very similar to the experimental setup in that has been widely used in our community. So where we start with the camels dataset, we took the 531 basins, and here the validation test and train splits are based on the day. We took 15 continuous and 26 static variables of past 365 days. Here, like this experiment was following that experimental framework, widely used in our community, because we wanted to make it comparable with the existing literature. That was the purpose. We only set up LSTM and TFT here because by that time there was already a paper or from Chopin's group who did a transformer setup in the same framework. So we just went with the LSTM and TFT. So basically, this is a benchmarking of TFT against the current LSTM benchmark. And here, using the past 365 days, we are trying to predict the 365th day, like the final day's stream flow. Now, this setup is repeated 10 times using 10 random initializations. And we took both ensembles, like based on the firstly we took the average ensemble, just taking the average of the prediction from these 10 variables. I mean 10 like models. And also, like based on the validation, we took the best performing model, and we just like it's a best validation ensemble. So all this setup is following this paper like by Freddie. So we, as I said, like we wanted to make this comparable with the existing literature. So the results of this setup,
Jinan,
yeah.
before you go on, So now are you still training one model per basin, or are you training one model for all basins?
No, yeah, this is like one model for a whole basin, like all 531 basins. Yeah. Thank you for the question. Like, yeah, it was an important information I should have clarified. Yeah, so this is one model for all 531 basins. So here the results shows, like TFT, he's like better, but it's very slight improvement. It's not a very significant improvement.
Sorry, just a quick follow-up on that. So you're not doing any fine-tuning, right? It's just one
No,
regional model?
no fine tuning. Yeah,
Okay,
just one, like one setup.
thanks.
So, yeah, the results here is like as you can see, like NSE of LSTM in case of average ensembling is 0.82 and 0.821. So it's like very slight improvement. And in terms of kg also, like it's very 0.005 improvement. Here like this is the distribution of both LSTM and TFT kg. Like we see that like the high performing basin, the number of high performance basin has slightly increased in case of TFT. Again, like this could be like, I would say like 10 out of all these 531 basin, something of that order. Yeah, again, like in the previous experimental setup, like we tried comparing the variation, or we tried to see the variation with respect to catchment attributes. Here, if you look into the variation with respect to mean elevation, as the elevation increases, the distribution of the TFT. I mean, here again, the TFT is blue and the orange color is LSTM. So the TFT distribution kind of improves, as we goes into higher elevation. Like in the lower elevation, in 0 to 750, like most of them, like it's the distribution is kind of similar. But as we go, like in higher elevation, it tends to, the TFT tends to shift rightwards. Yeah, one more thing, like here, again, we think the potential reason could be that like higher response time in those higher elevation basins, dominated by snow process and other slow rainfall runoff dynamics. We tried the same experiment with different sequence lengths. Again, as sequence length increases, there is a slight improvement in TFT performance, because we can see the distribution slightly goes upward. But in case of past 5 years, we see a drop in TFT performance, like potentially because by that 5-year sequence length, almost half of the training data set is lost. So maybe that data scarcity might be the issue, like, but I'm not sure, like we see a drop in TFT performance by the time we reach, by the time we took the sequence length of 5 years. So these are the results in both experimental setups. One more thing, like the first part of that study was published last year, and the second part, like we actually published this in two separate papers, like using experimental one setup was in the last year's publication, and the second one is now under review again in Journal of Hydrology. So the key takeaways in this study could be like the superiority of TFT performance were more prominent in that time series setup, were the first experimental setup. And adding attention can be a better choice for basins at higher elevations, or where the hydrological response times are high. And the attention can take advantage of longer sequences. So with that, I would like to conclude this presentation, and I would welcome any question, suggestion, feedback. Thank you. Thank you so much.
Thanks, Yunan. That was
Thank
cool.
you.
Great presentation. Well, I think we can move on to questions. Does anyone have questions for Sina?
I have a few if nobody else wants to go first.
I can start with this very quick one, simple one.
Sure.
In your architectural slide, so you showed the attention layer as explainable multi-headed attention. So I guess on slide 29, you show some features in your interpretability. So I guess those were extracted from your attention, right?
Yes. These were basically coming from this variable selection layers.
Oh,
So
okay. So you don't. So what does it mean when you say mask interpretable multi-headed attention?
so like mask means like just like as in a regular transformer, we mask out that one half of attention, like, right, because of like we don't want the past states to get information from the future states. So it's just that mask, and interpretable is yeah, because like here I think it would be a it is just like we can get a attention score. Like I think this is possible in a regular transformer also. I believe it's just the attention scores uh, for each time step that the model provides, and I believe that's that's the interpretable part of that this layer. And multi-head attention is like just we
Yeah.
have, yeah.
Because
So
my question is more, do you actually do something with the attention you compute and train on every model iteration? Because you say it's interpretable, but do you actually get something out of it that you interpret later?
it's just the attention score. Like that's the so let me go
Yeah,
back.
no, I know. What I mean is, for
Yeah,
instance, oh, okay, so you do actually okay, the look back. All right.
yeah, something which time step the model relies more on to get a particular stream flow value.
And I have a follow-up question on that. Is do you think using multiple head does alter the interpretability of the attention computation? Because there is some sort of a parallelized computation, then merging and all that. Do you think compared to using another type of attention, like self-attention, for instance, not multi-headed, do you think there is some sort of alteration of what you can actually get from that?
uh like I'm not sure, like like if there is any like difference or like advantage of using the other attention, other type of attentions. Yeah, because we like we did not compare with any other. This is the only model structure or architecture that we implemented, right? Like yeah, my honest answer is like I don't know, like if that would improve or not.
Okay, thanks.
While we're on the slide, go ahead, Alison.
Yeah, I had a question on that look back where it was like 1 to 12 months. Would it be larger if it were like 13? Like if you went to 13 months ago, it would be exactly a year ago. And is that
Yeah.
world
So
conditions are really
yeah, thank you for that question. Yeah, I think like that would be possible. Actually, I have different plot. Maybe I can I can quickly show that. Like there was some updates that we, yeah. So let me reshare the screen, and that might be helpful. So can you see this figure, like
Yes.
yeah, so here you can see that there is this is again the attention score by using past 60 months, like the past 5 years, right? So you can see that the seasonality in that attention score, like to predict there in the, like, here it would be like 13 or 14, past 13 or 14 months. Then again, like 2 or 3 months past the 24 months, again 2 or 3 months. That seasonality is reflected in this attention score when we use the whole 5-year sequences. So yeah, so it does depend upon the past, we like that rainfall runoff dynamics.
Got it. Thanks.
Thanks, Sinan. Could you go back to your slide 18, I think it was? Yeah. So you pass the input variables through your LSTM. And then what are you sending to the transformer? Are you sending the states of the LSTM, all 256 of them, or are you just sending a computed output, so a single value coming out of the LSTM? What are you actually sending to the transformer?
So it's the single value, like in the LSTM, all these the
All right.
outputs from each cell.
So effectively, what the LSTM is doing is it's taking 365 past values of the inputs,
Mm-hmm.
and it's converting them into 365 values of the outputs. In other words, it's doing some kind of it's doing some kind of 365 to 365 mapping, with the only main difference being that at the beginning of that 365 days, it has some initial state value, so it has an output. But I'm assuming that because your sequence length's 365, I'm assuming you're initializing your LSTM always to be 0, right?
Yeah, that's it.
Zero. So in effect, what your LSTM is doing a transformation from 365 to 365, and then feeding it to the transformer, as opposed to if you didn't use an LSTM, you'd just be feeding the input values directly to the transformer.
Yes,
That,
yes.
Does that make sense? Except that if you fed it to the transformer, you would be feeding not just 365 values, but 365 times however many input variables you had. Does that make sense?
Yes.
So you're actually taking let's say you had, I don't know, 20 or something input variables, dynamic time series. You're actually using the LSTM to compress them down to one variable, which varies over time. And then you're feeding that to the transformer. Would it make sense that that's the major difference in how you're adding the transformer to the LSTM to the transformer? Trying to
Yeah.
Yeah.
Yeah. So, all the variables, let's say, at time t minus 365, like all the variables go to the LSTM, and it will be essentially one output from the LSTM layer that from at this particular time step goes to the attention layer.
Okay. Whereas if you just did the transformer by itself, you would be feeding all of the input variables for 365 days. Is that correct?
Yeah. Okay. Like,
When you do the pure transformer, what are you actually feeding to the pure transformer?
So yeah, you mean in this setup, right? Like in the
Yes.
yeah.
Yes.
So here, yeah, like all the inputs are going into the transformer.
Okay. So effectively, what the LSTM is doing is a kind of a compression. It's taking whatever 20 times 365 values and it's compressing them down to 1 times 360. I'm just picking 20 out of my head, just if you had 20 input variables, whatever, right? Am I understanding that correctly? It's essentially doing a compression from a 20 by 365 down to a 1 by 365 before feeding it to the transformer.
Like let me I think it doesn't have to be one necessarily. It can be yeah.
Could
And
be multiple outputs.
yeah. So yeah, it's a compression in that sense. It can be 1 by 65 365, or like, let's say if we give like other like 50 or
Okay.
yeah, we can.
So, and because the LSTM is being initialized to 0 365 days in the past, would it be fair to say, I mean, you kept saying that you can attend to longer sequences, but I'm having trouble seeing that. If the LSTM only has a 365-day sequence length, beyond which it's initialized, at which point it's initialized to 0, I was having trouble understanding why you were saying that adding the LSTM actually gives the entire model the ability to look back further into the past. That part I didn't quite follow. Yeah.
So the idea was so if you just see the LSTM alone, like here the information from this LSTM at t minus 365, it goes to the next step, and like it's again whatever information received from the past time step, it like process that and pass to the next step. So it's like step by step, like so when you take a time step, it all depends upon just the value that is coming from the previous time steps cell, LSTM cell, right? So but in case of LST attention, like it is not necessarily the case. Like you can like even let's say you are processing the data at time step t, you still have the access to the information or the output from the LSTM at t minus 365. So even if you're processing at t, like you can use the information, what was the output of LSTM at t minus 365. You can use that. But if it was just an LSTM, like to process the information at time step t, you have to entirely, you are entirely depending upon the t minus 1 time step. So
Yeah, I'm afraid I don't quite see it the same way that you do. As far as I can tell, all of the information that's available to the transformer starts 365 days in the past, the way you've drawn the setup, unless there's something I'm misunderstanding. And what the LSTM is doing is just basically processing it or encoding it in some different form. But I don't see that the combined model actually has any more access to information than either of the models individually. I'm having trouble seeing that happens to be true. Okay, because at any point in time, if I'm making a prediction at time t plus 1, the information that comes into my entire system is only information from 365 days in the past. And the information processing inequality tells us that manipulating that information doesn't add any additional information. It just repackages it in a different form. So I'm wondering, because I was a little surprised to see that the performance benefits of adding the transformer didn't seem, honestly, to me, terribly significant. They were very very small,
Yeah.
right? And what I'm suspecting is that the benefits that you did get had to do with the fact that the LSTM, the added complexity of the added LSTM was actually just transforming the data into a form that the transformer was better able to take advantage of, and not necessarily because it had access to more information, because I can't see that it did over here.
Okay. Yeah. I think, maybe I have to look into that a little more details, like, maybe, yeah. My understanding was because of that, that the performance improvement was because of that particular, access to the ender sequence. But yeah, maybe, yeah, I'll follow up with you, regarding.
Sure. Yeah, I'd be happy to talk to you about it. Um, I like, you showed the CDF, or the probability distribution of performance. I wonder if you could do something interesting, which is here you're plotting essentially a statistical summary. Yeah, that one is fine, 25. Yeah. You're plotting actually essentially a marginal distribution, but I'm curious as to how many basins actually improved. In other words, you're providing a statistical summary, but if you did a pairwise comparison, right? If you plotted scatter plots, for example, I'm curious to see uh, uh, if you did scatter plots of LSTM versus transformer, or LSTM versus TFT, or transformer versus, right? How many basins actually improved and how many got worse? Because statistically,
Yeah.
that's going to happen, right? And then it would be really interesting to see in which parts of the country you got improvement and in which parts you did not get improvement,
Yeah.
and whether that corresponded to things like elevation. And you suggested by elevation band, but I'm curious to see what would happen if you did it by aridity.
Okay.
In the past, Luis, for example, has found that performance varies significantly by aridity, and it's quite possible that it's some combination of these two, right? Elevation and aridity, because the low basins are likely to be probably more arid basins, and the high basins are likely to be less arid basins. But I buy your argument that there should be some elevational relationship, but I'm wondering if you were to take it out in 2 dimensions, whether you would see more
Yeah.
patterns. Yeah. Does that sort of make sense?
Yeah, that makes sense. Yeah. I'll do that, like I haven't done it yet, but thanks for the insight.
And then my third question had to do with the fact that since you have this very strong annual cycle, you show the attention on an annual basis. I'm curious what would happen if you were to difference your data annually, right? In other
Oh.
words, you learn a model on top of an annual differenced model. Does that sort of make sense? If you look up time series analysis, this is years ago, but Box and Cox, if you have a strong periodicity, then one of the standard things they do is they remove the periodicity and then they build a model on the difference data.
Yeah.
And I'm wondering if you could use that to take advantage of longer attention windows, if you see what I mean.
So, like you mean like do that transformation before passing it as an input?
Doing the differencing and then learning and then using your models to learn to predict the signal on top of the difference signal?
From a like from a how I didn't quite like understood that like so it's like passing it as a separate input, or like from an implementation point of view, like can you explain?
Yeah, okay. So oops, sorry. Let me take off the blur so you can see my paper. Where are we? Background and effects, none. Okay. So let's say we had a trend, right? And then
Yeah, this one,
right.
yeah.
So if you were going to want to predict this, you would first predict the trend, and then you would predict, one possible approach would be you first predict the trend, and then you predict the signal around the trend, right? Similarly, if you had a similarly, if you had a periodicity and you had a signal around the periodicity, then it would make sense to predict the periodicity first and then predict the residual, right? So if you difference the data with the period of the data, then you would be pulling out the signal which is on top of the periodic.
Yeah.
Right?
Yes, yeah, I got it.
Yeah. So I'm wondering if the work that you've done here could somehow be extended to take advantage of much longer memories in the system, because right now you're only using 365 as best as I can tell, right?
Yeah, that's right.
But I'm wondering if what you were trying to do could actually be partly achieved by some kind of signal decomposition.
Yeah, I think yeah, like that might, it's something definitely to we're trying in the future, because yeah, right now like the entire model is trying to learn from all the signals and this periodicity and trend, like at once. Yeah, decompose. Yeah, that could definitely from my understanding it might improve the performance. Yeah.
So I guess my overall comment is we're adding a lot of complexity to the predictive model, and I'm interested in short description lengths. I want the most simple explanation for what's going on, right? And the additional performance gains that you're showing, if it were entirely up to me, I would go, I'm not sure that's entirely justified by putting all of this additional complexity to get this, very small amount. So I'm wondering if I've got nothing against adding complexity. I'm just curious about the ways in which we add it, right? In a way that somehow are as short description length as possible, so we do it efficiently.
Yeah.
I like the idea of combining LSTMs and transformers. I'm just, and that's why I was very interested in your talk. I'm just still wondering what the appropriate way to do that is, right? Because they both have strengths, right?
Yeah, I mean, I'm remembering the concept of Occam's razor, like if something can be achieved in using simple terms, like in a simplified way, that would be the best way, right?
Right.
Yeah.
So what I'm trying to do over here is understand what is the LSTM contributing and what is the transformer contributing, and you chose a particular way of doing it. You first stick the LSTM, the transformer on top. Presumably you could imagine doing it the opposite way.
Yeah.
Or many other kinds of things. And so, since you have a lot of experience with this, I'd be curious to see, what you're able to think up of interesting ways in order to exploit the strengths of both architectures.
Yeah. Thank you for like your this wonderful insights. Yeah, like as you mentioned, if you were to try a different set, like, architecture, like, LSTM on top of attention. We don't know, like, how the performance would turn up. Again, like, we haven't characterized whether, the added complexity, or if it is, like, as we were assuming, the access to the undersea and all those aspects, were they contributing the additional performance? That wasn't, yeah, we didn't characterize that. It was just, like, we implemented all this, okay, and we see that there is an improvement in the performance, like when we did.
So where are you taking this next? What's the next step?
Right. I mean, to be honest, like, I haven't like, thought about anything, because, this is not part of, I'm right now, like, I'm completely busy with my thesis and all, like, it's completely a different, like, it's this work is not a part of that at all, like, it's on a different story. So, like, I want to get back to this. Yeah, to be honest, I haven't, after getting this published, like, I haven't thought much about, how to take it forward. Once I am done with that, like, I want to put some time and thinking on this. Yeah.
Okay, very cool. Thank you. That was very, very helpful. It made me think a lot. Yeah.
Thank you so much for the insights and
So
We
is Roy your advisor?
yeah. Roy is my advisor. Yeah.
Cool.
Yeah, it's kind of, like, you are kind of my grandfather, I would maybe.
Very cool.
we have Tao Liu in the chat, but isn't able to talk right now and had some questions, so I'm gonna read it out loud. It seems there are more than 200 static features for each basin, and then some of them were selected before fitting to LSTM. And the questions are the following. How many features were actually selected or given larger weights, and what are they? What can we learn from the attention scores, which I think we answered. Also, I like your presentation, how do you make the structure and transition effect? That you can read this from the chat directly.
Yeah. So, I think, like, what he's referring here, like, by selecting a set out of 200 static features, is regarding the variable selection networks again. So what happens in this variable selection networks? Maybe I'll explain it once again. So for each time step, like, let's say we are taking t, each variable value is passed through this particular GRN, gated residual network, and we get a, like, a transformed output, represented, on top of it. And at the same time, there is another GRN, which takes a flattened input, like, using, that's represented in this symbol. And the C is just a context vector that is coming from the static covariate encoder. So it's optional. Let's forget about that for now. It's not needed actually. So the flattened input is passed, and after that, after passing through the softmax processed and softmax, we get a vector like, V chi or Vx. Let's call it Vx. So this Vxt is just a, vector that is the same size of the number of variables here. So now we are taking a, like a weighted sum here. So it's basically, like, this represent Vxt represent that weight for each variable. So it's basically, there is no, filtering happening there. It's basically a weighting, let's say, like a weighted sum. So, and this vector, it like, this is determined after the training, right? The training will take care of, tuning these parameters, and we can take out this particular vector from the architecture, and if we just, take an average of that, that will give the feature importance for each variable. So it's not, there isn't a filtering process, but it's more like a weighting. How many features? Yeah, so I think that would answer that. So that, yeah, from attention score, like I have already mentioned that, like which time steps are more important that we can. And in terms of presentation preparation, like it's all this, Microsoft PowerPoint. Just, I think there is something called transition here. Like I use this morph transition like to make that. So I try to, like to make it as interesting as possible. Yeah, that's all. And this morph transition helps a lot. It automatically do many, that beautiful transformation. Yeah.
Right.
Thank you.
One day you'll just come up with your slides and ask AI to just do like fancy transitions.
Yeah.
So you don't have to do it.
Yeah. Nowadays, like, yeah, things are like that. You just need to type in what you need.
Thank you
So,
for answering Tao's question.
So
yeah.
morph is part of PowerPoint? No, is this, yeah.
Yeah. This is part of yeah. There is a morph transition.
I
Like
see.
you can see my screen right here in this one. The transition. There is more.
I got it. Yeah. Thank you.
You just apply. Yeah. Thank you.
I think Joe maybe had some questions.
Yeah, for that dense layer, is it linear at the end there?
Which one? This one in the.
No, the one going into Streamflow at the very end in A. Yeah.
Yeah. It's just linear layer.
So it can actually predict negative Streamflow.
Yeah, it can actually predict negative stream flow. Yeah. So like after I think I have to double check that like we can remove all the negatives to zero, something like that. And also one more thing I want to mention, since you mentioned about that dense layer, like the output of that dense layer is actually we take we actually output 7 values. Basically, we use a quantile loss function here. So it's like we are predicting more sort of an interval rather than the actual value. So it just basically maps, whatever the output at this previous block to, seven values. It creates a vector of 7. And yeah, so to answer your question, like, it can predict negative values.
I'm wondering, is there like a reason you didn't use something like ReLU or?
I mean, yeah, I mean, like ReLU was a possible solution, but even without ReLU, it was I mean, there was some negative values which it was not like too much negative, or like it was not deviating that much from the actual hydrograph. So just a slight filtering at the end would do the trick, I would say.
Okay.
Okay, do we have any more questions for Sinan?
Actually, I have a question, but it's not so much about your presentation. But you mentioned that Xiaopeng had applied a transformer. I'm sorry, I've got a doorbell. Somebody else ask a question. I'll be right back.
Are you going to HydroML, Sinan?
No, not as of now. Are you going to?
No, I'm not. I think Tarun is going, but I would have thought that would be like a very interesting conference for what you do. It's exactly on point.
Yeah. I mean, I have presented this in, I think last to last year, HydroML. Even last year also I could attend in person, but this year it's a bit difficult, like everything is difficult this time.
Yeah, I know. I'm not too much on the inside of things where you actually see the budgets and all, but yeah,
Yeah.
it's
Like
all
in one
got this mail last Friday, like NSF is shut down. So
yeah. Like in one way or other, like it is affecting, many things. And especially, for graduating students, it's kind of very hard times in my opinion.
I imagine.
Yeah.
Did you get a postdoc position somewhere already?
Not yet, not yet.
Okay.
Please let me know, if anyone is looking for a postdoc.
Sorry, somebody, the mailman rang the bell. I'm just curious because I haven't actually seen that paper. So, so they did a head-to-head with LSTM and Transformer.
Yes, yes.
Can you just quickly, if you don't mind, summarize for me what they made their findings?
So, like it's the title is something like probing the limit of transformer. So it's basically, the experiment too I have mentioned here, like in the literature, like this one, based on Freddy's paper, like 531 Bayesian one model with this validation test and train split, same set of input variables, but they just used a encoder part of the transformer. So yeah, so if I go back to this, so there won't be that decoder on the right hand side, whatever the output, it is directly. So in that way, they just compared, the performance. They calculated the kg and NSE, all these matrices, and the results says the transformer is not outperforming LSTM. It's like a little bit lower than LSTM. So that's why I think it was like a benchmarking study, more sort of a benchmarking study. So still, like LSTM stays as the benchmark in this particular experimental setup. Yeah.
But I'm assuming they just did the statistical comparison. They didn't do a basin by basin thing.
No,
The thing that I was asking for to see how you
I don't think so. I mean, yeah, I don't. Yeah, it's more sort of a statistical comparison.
Yeah, I'd be really curious to see what you find out when you
Yeah,
do.
yeah. I will. Once I'll get back to this. Like I'll be in touch with you also. Like we can see like it would be interesting, but somehow I missed to create that plot, and it was not part of that analysis. Yeah.
No, it's not become standard in the literature, I know, but
Yeah.
so far people have been just very interested in how many decimal points can I move the median, and I'm
Yeah.
going, okay, at some point we have to stop worrying about that and worry about more substantial things. Yeah,
Yeah. I agree. Yeah.
very cool.
Thank you.
Thank you. Well, I think it's a wrap. So thank you so much for presenting. I'm going to stop the recording just now.